In this chapter, we introduce the F-test, a tool for evaluating the overall significance of a regression model. The F-test takes a broader view than the t-test. Instead of testing one coefficient at a time, it tests the entire model simultaneously. You have already seen the t-test, which assesses whether a single regression coefficient is significantly different from zero. It answers the question, does this one predictor matter? The F-test takes a broader view. Instead of testing one coefficient at a time, it tests the entire model simultaneously. It asks, is there any predictor at all that explains variability in the response? In other words, the F-test evaluates whether the observed relationships between predictors and the response are due to random chance, or whether at least one predictor genuinely explains variability in the data. Like the t-test, the F-test is a formal hypothesis test. It is most useful for multiple regression models, where we have more than one predictor variable. Let's look at the null and alternative hypotheses. The null hypothesis states that every regression coefficient, beta 1 through beta p, is 0. This means none of the predictor variables have any effect on the response variable. The alternative hypothesis says that at least one coefficient is non-zero, meaning at least one predictor variable is significantly associated with the response variable. An important nuance. Rejecting the null hypothesis tells us that the model as a whole is statistically useful. It does not identify which specific predictors are responsible. For that, we still rely on the individual t-tests. To carry out the F-test, we compute the F-statistic. The F-statistic equals the quantity TSS minus RSS divided by P all over RSS divided by N minus P minus 1. TSS is the total sum of squares. It measures the total variability in the response variable around its mean. RSS is the residual sum of squares, the variability that remains unexplained after fitting the model. P is the number of predictors, and N is the number of observations. Intuitively, the F-statistic is the ratio of the variance explained by the model to the variance left unexplained, each adjusted for the appropriate degrees of freedom. A larger F-statistic indicates the model explains a significant portion of the variability. For the decision rule, if the F-statistic is large and the p-value is at or below 0.05, we reject the null hypothesis. At least one predictor is significantly associated with the response. If f is small and the p-value exceeds 0.05, we fail to reject the null hypothesis. The model shows no significant relationship. On the exam, you won't need to look up critical values from the F distribution table. Instead, you'll be given an F-statistic or a p-value and asked to interpret it. The partial F-test extends the idea of the overall F-test to test whether a specific subset of predictors can be dropped from the model. Suppose we have a model with p predictors, and we suspect that the last q of them contribute nothing. The partial F-test lets us test that idea formally. The null hypothesis states that the last q coefficients are all 0. Those q predictors have no effect. The alternative says at least one of those q coefficients is non-zero. That subset of predictors does contribute something. The partial F-statistic is RSS sub 0 minus RSS divided by Q all over RSS divided by N minus P minus 1. RSS sub 0 is the residual sum of squares from the reduced model, the model that excludes the Q variables being tested. RSS is the residual sum of squares from the full model, the model with all P predictors. And Q is the number of coefficients we are testing for omission. If RSS0 is much larger than RSS, those Q variables do reduce the residuals, giving a large F and evidence against the null hypothesis. Why do we need the F-test if we already have individual t-tests for each coefficient? The answer comes down to false positives. When we run many individual t-tests, some p-values will fall below the significance threshold purely by chance. This is a false positive. Here's an example with 30 predictors. 25 of them have p-values below 0.05, appearing statistically significant. But with 30 simultaneous tests, it is possible there are false positives by chance alone. Look at these borderline cases. X6, X12, X14, and X25 all have p-values just barely under the threshold. Any of these could be false positives, appearing significant purely by chance. The F-test guards against this by evaluating all coefficients simultaneously. It keeps the overall false positive rate at the intended significance level, regardless of how many predictors are in the model. When the number of predictors p exceeds the number of observations n, it becomes infeasible to fit the model using traditional least squares methods. When least squares fails, the F-statistic cannot be computed. In this high-dimensional setting, alternative approaches such as subset selection become necessary. We'll cover subset selection methods in the next video. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.